Welcome back. All right, so let's continue with the momentum and try to finish off the chapter itself. So here I'm going to illustrate and piggyback on something that I did in the previous video, which was related to kind of special cases and elastic collisions. I can put up a link up above there. And I want to talk about kind of total mechanical energy in these elastic collisions, at least in perfectly elastic collisions, okay, that we have. So you can see here on the screen, so I put up the conservation laws in general. So we, of course, know that momentum is conserved. So that's number one. Then we know that kinetic energy is conserved when you have elastic collisions. But now for the third one, which is in red there that you see there, during a collision, there's also the total mechanical energy which is conserved, which will be between kinetic energy that you have and also the elastic energy due to the collision itself. We're assuming there's no frictions, okay? We're on one particular surface, so we're not dealing with gravitational potential energies. So we only have kinetic energy and then elastic energy in order to work with. All right, so let's take a look and break down this whole idea of the total mechanical energy. So the goal is going to be explaining this particular concept of the total mechanical energy in this particular video, and it is going to piggyback off of this whole concept of momentum and then focusing on elastic collisions. Okay, so what is happening within here? Let's try to kind of illustrate this as a whole. So imagine that you do have two objects. We know that the total of the momentum is always conserved. We know that the total of the kinetic energy is also conserved. But what happens during an actual collision itself? Because there will be an instant in time, okay, it might not be a lot of time, but a very short period of time, where two objects are going to collide. So if you imagine these two objects are going to be coming towards each other and they're going to collide at some point. Now, what this is saying for the total mechanical energy is the following. So we have initially a certain amount of kinetic energy. So that is not a surprise to us. Notice that this is the initial energy of the first object. Let's say that this is maybe the first object on the left, and then this is the kinetic energy of the second object, which is maybe the one on the right. So let's label this one as 1, okay, and then the other one as simply 2, so that you know and you can distinguish. Now, when you add these up together, the total mechanical energy is going to be now the following. So here is just the kinetic energy that you have after the collision. And we know that for elastic collisions, okay, of course, this must hold. And we talked about it. We even had some special cases related to this, as I pointed out in that link at the start. But then you have this particular term, which is the elastic. So this is the during the collision itself, right, the objects will actually slow down. So whatever it is, especially as they're moving towards each other, or they don't have to, they can certainly be moving away from each other, but one would have to be moving faster, the one that's trying to catch up, so that they actually do collide. But let's imagine that they're just going in towards each other and then they're going to collide. So then they're going to not necessarily stop, because it depends on their masses and then the speeds that they're moving at, but they are going to slow down. And then during that particular collision, so what we want to be able to say is, we want to say that the total mechanical energy, well, that still gets conserved overall in these elastic collisions. So we're not losing anything to friction or anything else. So if you imagine, this is what would be happening. So if I would draw a graph, and this is the total energy, okay, or at least this is the energy that we have, so maybe not total at the moment, and then this is time. So if time passes by, originally, so for in this particular case, we only have kinetic energy, and that would be the total kinetic energy that we would have. So as you would be going along, you would have a certain amount of kinetic energy, all right? So this would be for a certain amount of time until the collision happens. Now, in terms of the term that you see right here, which is the elastic energy, that's right here, which is 1/2 k times x squared. Again, if you maybe forgotten about elastic energy, I'll put up a link up above there for you. So that's the total amount of elastic energy that we would have. Now, before they collide, there is no elastic potential energy because there's no collision. There's nothing within there. Now, you can imagine that there's like a spring, okay, kind of connected to one of those objects, and then that spring starts to compress. And hence, you have this X. This particular X is the actual compression, and then that compression allows us to have a certain amount of elastic energy. Right now, we don't need that spring because as the actual objects collide, they can literally compress a bit, okay, and then we're looking for that particular X. So within this, initially this would be set at 0. So I can kind of draw this out, okay, and this is what you would have right there, where this is referring to the total kinetic energy, and this right here, the green, is referring to the total elastic energy. Now, as it collides, it is going to start to lose some of its kinetic energy. So it's going to start to lose some of this. However, as this is getting lost, the elastic energy starts to increase. And then when you're adding both of them together, so when you add this plus this, it is going to be equal to the total mechanical energy that you have. So although this technically is getting lost in terms of kinetic energy, it's not a loss, it's a transfer to this. So what happens is overall, and I'll try to draw it just above it, and then maybe, okay, will dash it. So this would have been kind of like the total that you have. So the total remains the same as you would have in any kind of conservation laws, right? So this would have been the total, the summation between the two. And as you're moving along in between them, so back to the kinetic energy, it's going to try to decrease, okay, as much as possible within here, okay, until eventually, this keeps increasing, all right? So then eventually it just crosses, it will have a peak right here, and then that elastic energy again is going to be given out, okay, as the two objects collide, and then they separate back up. So then there will be no more energy. And this, okay, no more elastic energy. And then this kinetic energy will go to some minimum, and then again, it's going to kind of pick up and then come back to its original, okay, that you have. So that would have been the view and then the transfer in between one and the other, but the total amount always stays the same. Now, please note, I kind of labeled this, so you might think that this is 0. So this indeed, okay, for elastic energy will be 0 at a certain point, but for kinetic energy, what will happen is, okay, it may not necessarily go to 0. It will just go to some minimum that you would have. So it would go to a minimum and then it would go back up. But the sum between the total, okay, would always be, okay, right at the top. So that's the whole understanding of this. So this is what we mean during collisions, during elastic collisions, that the total mechanical energy remains conserved in between them. And this equation right here is during a collision, right? So after they separate, this term obviously is now gone. There is no more stored in elastic energy. And really, okay, it would just go back to our kinetic energy conservation that you would have. So that's what happens. Now, just a note I want to give you. So there's two kind of important items when you have a maximum compression, right, of that particular spring, or at least the maximum amount in terms of elasticity that gets passed along from the kinetic energy. So there's two cases that can happen. So here I wrote V1 and V2. Now here I am referring to, this is during the collision. All right, so what happens during that collision? So these two, at the maximum amount of compression, will be equal to themselves. So they'll be moving at exactly the same speed. So what it says is that in this case, what happens is that the maximum compression during the collision, the two objects move together momentarily at the same velocity. Okay, but it may not necessarily be 0. So they're just moving along, because if they have different masses, they have different initial speeds or velocities, okay, they will collide, and then momentarily at the maximum compression, they will move at the same speed. Okay, if they weren't moving at the same speed, then one would be catching up to the other one, or one would actually be already bouncing off the other one. So during that collision on the maximum compression, they'll be moving at the same speed. Now, the very, very special case is that during a collision, it can also happen that they might come to a complete stop. Okay, now coming to a complete stop is only really going to happen if they have the same amount of mass and then they started off with the same amount of initial speed. Okay, so they're coming in, boom, colliding, stopping, bouncing off momentarily, and then they're coming back and they're going to be moving back to the same speeds as they were coming in. But that only happens with a very special case with the same masses and the same initial velocities. If they are moving with different velocities, okay, to start with, or different masses, then they don't necessarily stop. They have a relative speed, which might be 0 to each other, which means that they're moving at the same speed, and then they've compressed the spring or compressed whatever it is in terms of their collision, okay, to the maximum. So that's what happens. So let's take a look now at an example and try to do a nice example here for us so that we can utilize the equations overall and then make these calculations, and hopefully you will know how to use them. So here our setup is two bouncy carts are rolling towards each other on a frictionless surface. We don't want to lose any energy due to kind of heat on the friction side. The one on the left has a mass of 2.5 kilograms, and the one, and it's moving at 3.2 meters per second to the right. And then the one on the right is a bit heavier, which is 3.5 kilograms, and it is moving at 5.5 meters per second to the left. Now, when they collide, okay, a spring has a stiffness, so there's some kind of a spring in between them, which compresses at 6.5 times 10 to the 4 newtons per meter. Okay, so that's what the stiffness is. All right, so let me just draw out, okay, in fast forward fashion here, what that setup is. So here's the setup that is coming in from the question, and this is what they're trying to ask us. Okay, so right here. So what is the compression of the spring at the moment when the heavier cart is still moving left at 5 meters per second? Notice initially it's moving at 5.5, so as it collides, it starts to slow down, but it's still moving at 5 meters per second to the left. All right, and now we want to know what the compression of the spring would be in this case. So in order to solve these style of questions, still don't forget that the conservation of momentum always holds. So you can use that whenever you are, for example, missing some piece of information. So let's say what we do have. We have all our initial information. So we have the initial masses, okay? We have the initial speeds, that's what we have. We have the K right here. And then we also know, and this is coming from right there, this would have been our final. So in terms of our final one, so this is going to be V, okay, and that's final number 2. All right, I'm going to call this one number 2, and then let's call this one number 1. That is the actual speed that we have. All right, so once we have this information, if it's asking us for the compression, that would be right here. This is what we want to find. Now, if you're looking through the entire thing, we have this. We certainly have this. We have this because we know the final speed, but we don't have this term right here because we don't know what this is yet. We know K, and we're trying to look for X. So how would I possibly solve this? Well, I'm going to use this equation. Right, so I can substitute all of the pieces of information. I'll have this, which is the left-hand side. I'll have this on the right-hand side. I do have the mass, and then I can find out what that speed is. So that's going to be the first thing that I'm actually going to do. So let's do that. I'm going to do that in fast-forward fashion, and then let's try to solve for that speed of the one on the left, okay, the blue one, in this case, the way that I drew it. All right, so here it is. We have the speed, so it's still moving to the right. Now be careful because I originally put in, okay, so we have to put in these, okay, with the proper signs for the momentum, okay, so that it is moving right or left. So right, I'm going to assume it's positive, left, it is negative. And then what I'm doing is I'm just calculating this. I'm shifting this over on the other side and then dividing by 2.5. So that's what you see right there. So I get 2.5 meters per second, which I guess is to the right. Now that I know this information, I can now plug in all of these. So I know this, and now I know this, this, and this. And then the only thing that will be missing is my X, all right, or which is the compression, okay, of the, let's say that there was an imaginary spring in there. Okay, so I'm going to do that next, okay, so let's do that in fast forward fashion, and then I'll be right back. All right, so after the calculations, okay, so this is what we get. Okay, so that compression was 2.1 centimeters. And then what I ended up doing is just calculating the kinetic energy in the beginning, calculating the kinetic energy at the end. So those are the two values. When you bring this over, so those subtract. And then I took this 2, multiplied it right there, and then I had to divide by K. And in order to solve for X, okay, or for the compression, I had to take the square root of both sides. And that's exactly what I got right there. All right, so that finishes that component for us. Now for part B, it says, what is the maximum compression of the spring during the collision? So during the maximum, so if I want to be able to solve this right here, then I am not given what the speed is, right? So now I will have to find out. But during the maximum, what do we know? During the maximum, this is from the 2 little notes right here, we know that the final speed, okay, during that maximum is the same for both objects. So they come and they travel at the same speed. So how will I work with that? Well, I am still going to be using exactly these two equations, so it's going to be exactly the same thing in here. So let me just give you the gist. So I'm going to just copy this, bring it just below, and paste it back in here. And what's going to change now is, so from right here, so from this equation, nothing changes on the left-hand side. So the left-hand side remains the same. So this is identical. But the right-hand side, this right here, will now change because the two speeds are the same. So what you can do is you can just simply say m1 plus m2, and they're moving at the same speed. So you can factor out that v, and I'm just going to call it f instead of f1 and f2 because they'll have the same speed. So notice now, because we know these two pieces of information, we know the masses, we can certainly find out what that speed was in between them. So let's do that first. All right, so the first thing that comes out is that it looks like, and it probably kind of makes sense because the one which is on the right is bigger and it also is moving at a faster speed. So it's going to tag the one, okay, coming in from the left. So what's going to happen is as they're coming in, they're going to collide, and then this one will kind of take over and they're going to start shifting in to the left. So hence that's why you see the negative sign, because they're moving to the left. And obviously the speeds are slower now than they were before. So now that we have this information, we can now substitute this back in into right here. So now I know this and I know this for those. So I can calculate this we already have. Okay, I'm going to recalculate this and then I can solve for that maximum compression. All right, so let's see, what that will give us. I'm going to try to do that right now. All right, so there you have it. Okay, so the maximum compression was 4.1 centimeters, and that's going to be kind of the maximum, and then it's going to recoil back, okay, and then they'll separate, okay, afterwards, okay, as they're going through. All right, so that is it for this video. Okay, so this is the total mechanical energy for perfectly elastic collisions, and then trying to see and incorporate elastic potential energy as well. Okay, thanks for watching. We'll see you in a future video. Cheers, everybody.